Welcome everyone to this session where we're gonna see how we can emulate a Game Boy using .NET 6 and C# in this case. It's gonna be a wild ride because I'm gonna take you all back first into the dusty hardware manual and explain how the thing works, because you need to know how the hardware works before you can emulate it in software. But before I start, you can't talk about a Game Boy without doing this one. And a little bit about myself. So my name is Wesley. I'm a coding architect at Experience in Belgium. Trying not to spend too much of my hard-earned money on retro gaming consoles, but I fail because I recently just also bought a Nintendo, a classic one, not a small one, but an actual unit. I also love to play around with technology, soldering stuff, and finding out how things work. That started when I was very young, much to my parents didn't like this because I basically took apart every radio that I could find and then tried to put it back together, and sometimes it worked, mostly it doesn't. So we had to buy a lot of radios when I was young. Now, I have to give some credits first because some of the people here that visit NDC London might have seen a talk similar like this one, because when I saw David Whitney's session on the same topic, I got inspired to do this as well, to give this a stab of my own. But I also saw on YouTube another session by Michael Style, who really goes in depth about the hardware of the Game Boy. And these sessions are amazing to see. If you get the slides afterwards, all the links are in there as well. But there's like a whole series of the ultimate something talk. So I do recommend this one if you're into Game Boy. There's also one about the Atari, I think, about the Commodore 64. Great talks. You must see them if you're into the retro stuff. Now, as I mentioned, I saw these sessions, especially the one from David, and I thought, ooh, now this sounds like a very fun project to spend my time on. So I got into the Google, I searched for some hardware material, and I found the original document for, I think it was for Nintendo in America, to have them create games as well. So let's first dive into the hardware specifications of the DMG-01 or the dot matrix Game Boy. If you've never seen one, then this is the unit, what it looks like. This is what it looks like in real life. Still a good, decent thing, still works after all these years. Amazing stuff. And it has a very, very powerful 8-bit Sharp SM83 CPU that runs at 4.19 megahertz. Not gigahertz, not even close, but not really, and I'll tell you later why. It has a whopping 8 kilobytes of work memory and also 8 kilobytes of video memory. It has also a boot ROM to start up the Game Boy, which is 256 bytes. A nice tall 2.6-inch LCD screen with 4 colors and a resolution of 160 by 144. Yeah, that's not even 1/4 of HD, but it worked for that time. And for audio, we have 4 channels, 2 pulse waves, 1 noise, and 1 wave sample. If you open it up, I don't recommend it, but if you do, this is what it looks like inside. So we have, let me try to, I have to wake this thing up. Hello? Yes, that's the CPU. And then we have the memory chip here, and then the video RAM over there. And if we look inside the CPU, it's actually a system on a chip. So the CPU, the DMG CPU is actually a Sharp, and I'm gonna read this because I can't remember that one, LR35902. That's why we refer to it as a DMG CPU. But it is a system on a chip, and it has multiple items. It has the actual CPU, which is the Sharp SM83. It has the ROM, the boot ROM, an audio processing unit, and a picture processing unit. Now, The system alone, if you would power it on without one of these, it's not going to do a lot. It's just going to show you a blank line, a blank block. So you have to put in a cartridge, which looks, if you open it up, again, like this. Somewhat like this. There are multiple variants of these. Why? Because the earliest cartridges only had the ROM inside. So the ROM contains your game, the game boots, and then you start playing it. But that only works with games that are have a maximum size of 32 kilobytes, which is not a lot. If you want to have more enhanced games, like the Pokemon series, you need bigger cartridges. But the problem is that the Game Boy can only address 32 kilobytes of ROM in this cartridge. So, clever trick that they used to do in the days, they swap out memory banks with something called a memory bank controller chip, which is that tiny one over there. And then in this case, you can also see that it has a battery inside, which allowed you to save your games. So it had a RAM chip inside as well, and then the battery is used to give it a low power state so that if you turn off the Game Boy, it still holds that memory for you, so that years later even, you can still continue playing your games. Some of the most advanced cartridges even had a real-time clock inside, which used the battery as well, so that your Pokemon could evolve even if the Game Boy was offline. Well, shut down. Now, this is about the hardware. So the games, if you're going to emulate those, we're just going to download a ROM. You're not supposed to do that. So what you can do instead, because I want to make sure that Nintendo is happy with me, you get a cartridge like this, and you get a magic doodad like this. And then you can plug this device in. This even has a USB-C connection, and then you can dump this cartridge onto your system. That's the legal way of emulating games. But I'm sure you can find other ways as well. So we have our games. Now we have to build our system. And let's start by building the most important part of our system, which is the CPU. And the CPU is the SM83, and it's heavily based on a chip from 1974, which was way back before the Game Boy was also released, because the Game Boy only came out in 1989. And it was based heavily on the Intel 8080 CPU, which was well known at the time. Every developer knew this CPU, could program against it, mostly in assembly, but they knew how it works. And then a little bit later, in 1976, the Zilog Z80 was released. And if you remember, if you were there at the time, I wasn't, I'm not that old, then that chip was really, really, really popular. Because it actually took the Intel 8080 and it added another set of CPU registers, basically doubling the power of the thing, while being completely backwards compatible with the Intel 8080. So every developer back then could program immediately for this CPU as well, and then learn how to improve their knowledge at the same time. The CPU was so popular that it was actually used in things like Roland Jupiter 8 synthesizers and also the Pac-Man arcade cabinets. So really, really popular CPU at the time, and very powerful. So this should have been a perfect candidate for our Game Boy. So Nintendo decided to contact Sharp to make something else. Again, heavily based on both the Intel 8080 and the Zilog Z80, but also a little bit different. Why is it different? Because this one has only the registers from the Intel 8080. It doesn't have the double set of registers to keep the costs down. But Nintendo and Sharp said, there are some really, really good instructions available in the Z80 that the Intel 8080 just doesn't have. So let's borrow these instructions as well. And then they added some extra instructions that doesn't exist in the original CPUs, mostly for looping inside high memory. Now, when I talk about these registers, these are the ones that we have, so it's not a lot to work with. These days we have a lot more registers. These are all only 8-bit wide, so you can store numbers in these ranging from 0 to 255 or minus 128 to 127. And you have the A register, the accumulator one, the F for flags, and then we have B, C, D, E for general data or addresses, HL mostly used for addresses, and then of course a program counter, which points to the next instruction that the CPU is going to execute, and a stack pointer to point to the stack space in memory. And for flags, those are typically used, if you don't know, to keep track of state in the CPU while performing instructions. And in this case, we only have actually 4 flags, which is also not a lot compared to other CPUs. But the most important ones are there, called the Z, the 0 flag, which is set to 1 whenever an operation results in a 0 result, typically used as a precondition to jump after a comparison. We have the N flag, which is called the negative flag, but you might think it's going to be set when something becomes negative, but in this case, it's actually being set if you perform a negative instruction, like a decrement or a subtraction. So it's a bit different. And then we also have HN, which is a half carry flag used for decimal addition, which is a pain to emulate. And then the carry flag, if you go over your 8-bit values, then you have to set the carry flag as well because your result became larger than 255. Okay, these are the basics for our CPU. Then let's see how can we get something on the screen. So the picture processing unit is heavily based on the one that they used in this device, the Nintendo Entertainment System. Because huge popular console in both Japan, America, and Europe. So they knew how this works and said, let's use that one as well, that system in the Game Boy as well. And when they put it in the Game Boy, because they don't have that much power to work with, and it also needs to run on 4 batteries instead of on AC power, they had to limit the capabilities of the picture processing unit, which results in only having 4 shades of gray. But because the screen is a green, originally a greenish LCD, you get these lovely shades of green instead. And then whenever you want to put something on the screen, everything that you want to show has to be organized in little tiles that are 8 by 8 pixels in size. And everything also needs to fit in the memory, in that 8 kilobytes of memory. If you go over, it won't show up on the screen. And here you can see an example of the tile set for a particular game. And anyone has a clue which game this is? Sorry? Yeah, it is Tetris. You can kind of make out the parts of those dancing people at the end. If you've never seen the dancing people, you never finish Tetris. And you can see here as well, if you want to display text on the Game Boy, you have to include your own fonts. So there's no fonts inside, you have to do everything yourself. So that's one, our tiles. But then how do we get something on the screen? And that happens in different layers. So we have a background layer, which is 256 pixels large in square, which is 32 tiles. And we can only show on our LCD 166 by 144. So our background is larger than we can display. So what we do, we set a viewport using 2 registers, the screen registers. We can say we want to only display a part of that big background map, and that results then in the screen that we see on the right. And then you can see there's a white area at the bottom. And in this case, in this game, Super Mario Land 2, that's used to fill in with status effects. So this is called the window layer, typically used to get status on the screen, like number of lives remaining in this case. You can also see the amount of coins that you gathered, amount of enemies that you've vanquished, and then the amount of time left in the level. In some games like tennis, the window layer was used to pop up Mario in the top of the screen saying that you went out of bounds, or when it's deuce, then Mario popped up and said deuce. But with these two layers alone, it's not going to be a very fun game because nothing's moving. In the next slide, nothing's moving as well because I didn't include a video, but we'll get to that later. But we have to add some sprites as well, because sprites are the things that move around on the screen. And these can only have 3 colors instead of 4, because the 4th one is transparent. And you can only display up to 40 sprites in the entire screen at the same time. And of those 40, you can only have 10 on one scan line. And a scan line is 1 pixel in height. So it could happen if you have a very busy game that you get some flickering effects because there's too many things going on at the same line. So a lot of times they just decided if there's 9 items on a certain area, then they don't draw the 10th one. What also happens typically is if you see in this game, for example, the coins that you can pick up as Mario are not sprites. Because if you have a lot of coins to pick up, it would have a heavy impact on the number of enemies that you can also display at the same time. So coins, in this case, are typically part of the background layer. And then once you hit them, the background layer gets updated so that that coin is removed. It's a neat little trick that you had to do as a developer to get stuff working on this thing. That's our picture processing unit. Let's now see what we can do audio-wise. So, as I mentioned, we have 4 channels. The first 2 are similar. So, the first 2 are pulse wave channels, and they do the typical old computer sounds. And the first channel of these is typically used for special effects. So, if you pick up a coin or something, that one gets used to play that coin sound, which also means that your music is going to be a little bit different because you're missing one of the channels. The reason why the first one is used for sound effects is because it also is the only channel that's capable of producing more sweep-like effects to get like phaser shots or space sound effects things. Now, if we have a listen to one of these, if it wants to play, there we go. This is what it sounds like. The next channel is the noise channel. And noise channel is, if you have a very old television set and you had no cable connection to it or the antenna failed or something, you get like this nice snowy screen, and then it was like a effect. For people on YouTube, that was me, not your connection failing. And this noise effect channel is typically used for percussion or explosion effects. In this case, we get a nice march drum. Well, nice. We had to use whatever we could use to make some sound out of this. And then the 4th channel is a wave channel. And this one is a bit special because if I talk about waveforms from a music producer point of view, think of this as the sawtooth, the square wave, triangle wave, things you can also just draw yourself and then reuse to form some music. Some people went really far with this and actually created voice samples, which is on the Game Boy as well. I think you can, again, heavily used in Pokemon for Pikachu, for example. In this case, it's more like a buzzy sound that you're getting. And then if you combine the 4 channels together, you get a lovely sound. And some of you might know this music as well from Pokemon. Okay, so we have our CPU, we have our picture processing unit and our audio processing unit, but these things need to work together. And in modern CPUs, we have like interrupts and I/O ports, so you can easily say to your video card, hey, you need to do this, or to your sound card, you have to play this. But the Game Boy is a very simple system which uses memory-mapped I/O, which means that in that address space of 64 kilobytes, because it has a 16-bit address bus, it has to be able to address everything, which means, in this case, our first 16 kilobytes typically points to the ROM bank 0 of your game cartridge, and the next bank, next 16 kilobytes, goes to bank 1 up to FF or 255 using that controller switch. Then we get the address space for our video RAM, external RAM, which lives on the cartridge, so that's holding your saves, and then the work memory as well. Then there's a section called Echo RAM, which is a bit special. It was actually not used, but because how the hardware is created, it maps to other spaces of the Game Boy hardware, and it copies, well, it doesn't copy, but if you address that memory space, you actually get data from another address space. It's not supposed to be used, but people actually use it anyway, and sometimes it results in a crash. And the final green bar, if we zoom in what's in there, that holds our sprite table or object attribute map, the I/O registers to interact with the serial port, to interact with the joystick on the device, and to interact with the video and the APU. And then we also have something called high RAM, which I will talk about later as well. And finally, but not least, the interrupt enable register. Because if you don't enable your interrupts, nothing will happen. Okay, we also know how to interact with this thing. Now, if you fire up the Game Boy, the first thing that will run is the boot ROM. And the boot ROM looks like this. It's a bit small, but don't worry, I'll guide you through what happens here. And this is the actual original, sorry Nintendo, source code for the assembly in the boot ROM. It still amazes me how the community was able to get this source code. It's a story that I've been told. I like to believe it because it's so awesome. Someone opened up their Game Boy. It didn't work anymore, I hope. And they desoldered the DMG CPU, took off the plastic cover until they saw the actual die of the CPU, zoomed in with a microscope, and then somehow decided that must be the boot ROM, and that must be a 1, and that must be a 0. And 256 times later, this came out. Some people do have way too much time on their hands. But here we are. We have the source code, which is nice. Now, what happens is whenever you turn on the Game Boy, the first thing that will run is a little loop at the top to empty your memory address space. It will also set the stack pointer to the first position. And then we have to initialize the sound registers, because at some point, what we're going to do actually is we're going to scroll down the Nintendo logo, and then when it's at the middle of the screen, you get that tube chimes, the pa-ding sound. So we also have to set up that Nintendo logo, and that's actually stored here, the Nintendo logo. So we also have to decode it first, because while it's stored over there, it's also stored in your cartridge. More about that in a second. So we're scrolling down that logo all the way to the middle of the screen, and then you'll see that there's a gap between the scrolling because right before we hit that end of the screen, we're playing those two sounds. And then, again, here's the Nintendo logo, and we have to compare it with the logo that's stored on your cartridge. Because what happens if you decide to not pay Nintendo a license and you want to build games? You're legally not allowed then, in that case, to use their logo. And if you don't use their logo, your game will stop. It will not work. Your Nintendo logo will actually stop running here and will end up in a loop so that your game never starts. So you have to pay Nintendo a license, include the logo on your cartridge, and if it matches exactly that the boot ROM has stored as well, then it will continue. It does also a little checksum calculation at the end, just to make sure that the cartridge is fully inserted, so that you don't get garbled data later and a very bad game experience. And then the final step here is to disable the boot ROM, and then it will switch that first 256 bytes with the actual cartridge contents and start up your game. All right, we know enough of the hardware. Let's start actually, okay, some things decided to pop up on my screen, fine. Let's start emulating the Game Boy. And when you emulate a system, any system, you typically start with the CPU, which means that we have to look for some information about the CPU and the instruction set of that CPU. And there's a nice person who put a nice graphical table on the internet containing all of the different instructions and what they mean and what they need. But I noticed something on that web page. It has JSON. So what's inside of the JSON file? Well, it has a list of opcodes. In this case, we have the 0x10 opcode, and it also has the name of that opcode. In this case, it's the stop instruction. It also says it's 2 bytes long, which takes 4 cycles. It has 1 operand, it's an immediate instruction, and so on and so forth. Now, with all these instructions, we can then build a system that reads this JSON file, translates it into runnable code, and then use that to emulate our CPU. Oh, and by the way, the stop instruction is a bit special. It actually halts your program completely, doesn't run anything. It's used to preserve power, and then it starts again your CPU whenever it receives input. So you can basically use this whenever you're pausing the game, and then if you press start again, then it will continue and then start running your CPU, and meanwhile, your battery is not used that heavily in the system. All right, we have our opcodes, we have our JSON file. Let's start writing some code. And what is a CPU? Basically, it's an endless loop that runs instructions until there are no more instructions to run, or until you switch off the Game Boy. In this case, our Game Boy power toggle is a cancellation token. So we can just cancel the token, and then that will stop our CPU from running. And again, a CPU has a program counter, which is in the beginning set to 0, first instruction, and it will every time fetch the next instruction, execute it until we end somewhere. And what else is this execution thing doing? Well, it's basically a gigantic list of switch statements, at least in my first version of the code, where you look at that name of the instruction, for example, the no operation, the stop, halt, disable interrupt, enable interrupt. In this case, you can see not a lot was implemented yet. These are placeholders. But let's dive into some of the instructions that I did implement. But before I do so, note one thing here, the nice if debug entry, because I still had no video output, I still had no sound output, I just had the CPU, and I needed to be able to see how it went. So I outputted every instruction that I was about to run, Not the best thing to do if you're emulating a system, because this slows down the system to a crawl. But for debugging purposes, that works just fine. So these are the ones that I did implement at that stage, mainly the load instructions, because you have to get data from the cartridge in memory or data from memory into another register. You have to be able to add data together, to subtract data, to compare, and some stuff like that. And then if you look, for example, at the load instruction, I was very, very happy with my comments back then. And then a load instruction does nothing more than decide which is the source of data, which is the target of the data, and then move source to target. That's it. Because we're really working on the hardware level here. It's typically very basic stuff that we're doing. And then in some cases, you also have to update your flags. So this was already quite an effort to make that work, to also get to this stage. Did it actually work? So I pressed F5 in Visual Studio, and I did find the boot ROM code. So I just said, look, try to run this. And this was my console output. It started doing something, but was it doing the right thing? So if we look at the original code from the boot ROM, remember the first step was initializing the RAM. What we're doing here is, you can see on the left is the console output. So we're actually doing exactly the same instruction, loading the stack pointer with the highest address. So we initialize our stack pointer. Then we XOR the H register, which means it gets a 0 inside. And then we load the HL register with the top address of the memory chip. Here in the assembly, you get a jump label, address 0007. On the left side, we don't see that because it's just executing code. And you'll see you're loading that 0 value in the memory address HL, which is 9FFF at this moment. And then it immediately decrements HL to 9FFE. That's one of those SM83 special instructions to quickly loop over an address space. It then compares in the left part of the HL register a certain bit to see, did we reach the end of the address space that we want to clear? If not, then it jumps back to the top and it keeps on decrementing until it reaches that bottom of the memory chip. And as you can see, the loop was working. So it's actually doing the thing that it's intended to do. So, okay, we have our first success. Let's move on to the graphics. And filled with enthusiasm, after a few nights of work, seeing that first console output, I thought, all right, back to the hardware manual. I start reading about the picture processing unit and everything that's related to it. And then I found out that I made a very, very big mistake. Well, you see, I forgot about one special thing called timing. Yeah, there's timing registers. There's timing interrupts. There's the actual hardware timing that you need to emulate if you want to accurately emulate a device. I'll go over this slide in a second because I forgot to mention this in the beginning. I did say that the CPU runs officially at 4.90 megahertz, but these chips have special timings. And the memory chip cannot work at 4.90 megahertz. It actually works 4 times as slow. So your CPU is bound to the speed of your memory. There's a tiny crystal inside this machine which generates a pulse every 1 megahertz. And when that pulse goes high, then some things can happen. And then when that pulse goes low again, then it's safe to read data. So this is really on the hardware electronic level that you need to work with a Game Boy, but also need to emulate the Game Boy, because your CPU is not going to wait on your graphics card, in this case, to say, hey, I've done painting, continue please. In this case, that pulse sends really a pulse to all the systems, and they react at almost the same time. So when we are emulating, we also need to give every system part a chance to react. And I was just thinking, okay, I have my CPU, and at some point, my screen buffer is filled, dump on the screen, and go time. But that's not how this thing works. Because the the Game Boy was based on the Nintendo, the picture processing unit, which also means it was intended to work on a CRT device, an old television. And how does a CRT device work? It has an electron gun that shoots electrons on a screen, a phosphorus screen, which lights up the right colors. And it does that by really going line per line all the way from top to the bottom, and then it goes all the way back up to the top. But it is not perfect, and it will not hit your screen dimensions. It will actually overshoot a little bit first at the top, then also at the left and the right sides, it will not be perfect. And then at the bottom also, you have like a blank area where you don't have a picture, but you do have some time that you're spending in there. And these areas are called horizontal blank and vertical blank. And the Game Boy uses that same information to also have phases where you do something in your GPU. For example, before you paint the screen, there's a phase called Object Attribute Memory Search, which means before I'm going to draw this line, you need to make sure that all the sprites of that line are in the correct place in memory. And that's your phase OAM search. Then, when we hit our first pixel line, actual pixel that is going to be displayed, we're entering pixel transfer mode, where we transfer the pixels prepared to the screen. And during this time, nothing can change. So you can't jump at that moment as a character. Enemies can't move because they're fixed in that location. And then at the end, when we're done drawing, we have a phase H blank called, and then that can be used to update the time in the level, update the score, update the sound, and something else. During these times, a lot of the data and registers are locked so that you can't change them, which is why we have that high RAM, the small area in the memory map register, because this is the time where you can only use high RAM to loop over stuff. Now, after reading all of this information in the manual, and it's quite a heavy manual, I was thinking, my God, that's a lot to process. This is really not the place where I want to be in, because I was thinking this is a fun hobby project, not one that's going to consume months and months of my time. So it's time to look for a solution. And yeah, there's not really a market for emulating a Game Boy, so there's not a lot to be found on Stack Overflow. But luckily, there was this person that did the same session, David Whitney, and he published his source code on GitHub. So I looked at the source code. I found out it's also mentioned during his session. It was based on a Java emulator, basically. He ported it to .NET Core 3.1. So I said, in that moment, let's go over to .NET 6 because it's new and fancy. And also added sound support because David tried some stuff, didn't get it to work. I took another stab at it and somehow managed to make it work in the end. A lot of things were already there, but the actual sound driver for Windows was missing. And also found a little bug in one of the channels that was already existing in the Java version, and also fixed that one at the same time. And also the version that David made with Windows Forms had a little bit of a timing issue, especially when you start adding sound. It really slowed down the game. So I redid how how the picture processing unit works on the screen in Windows Forms so that it could run a bit faster. So, okay, let's try to run a game, and okay, we get the title screen, we get sound. In this case, you can't hear the sound because it's an image, but we got something resulting here, and then I wanted to play Tetris. I pressed start, and nothing happened. So that was really strange. I couldn't even move the cursor to two-player. Nothing did anything. The sound was playing, the demo of Tetris started playing, so the game was running fine. It just didn't accept any inputs. Huh, that's weird. How can we debug this? Well, the first thing that you can try is just load another game. So I loaded up Super Mario Land. Again, title screen, I press start, it started working. I could play Super Mario Land just fine. So why did Tetris not work? No, that means that we have to somehow set a breakpoint in our CPU to find out why it's not really reacting the way it should. But yeah, this is assembly land, so that means that we're gonna have to step through a lot of opcodes. For example, if you look at that same simple loop in the beginning, this is clearing 8 kilobytes of memory, which is 8,192 memory addresses. This tiny little loop of 6 instructions would already take you about 24,000 steps to debug. Yeah, that's not gonna work. If I'm gonna wait around for that one, I'll grow a beard, and trust me when I say that, I don't easily grow a beard. So that's not really how we're gonna wait, how we're gonna be able to debug this game. In this case, you have to rely on your knowledge, really. And I happen to know Tetris. I used to play that game a lot when I was a kid, and I remembered if you had 2 Game Boys, or a friend with a Game Boy, and if you had a friend, and a link cable, and both of you had the same game, you could fire up those Game Boys and play Tetris against each other using that link cable. So to know that there are 2 players, there must be some form of communication already happening when you start the game to know that you can play against someone else or only can play alone. So maybe that's why Tetris doesn't work. Aha, that's it. So again, I went back to the manual, and the manual has a nice flowchart about the serial communication part. Oh wait, that doesn't work. I have to, this one. So it actually says what happens when you communicate with the serial device. I had another look at the code and saw that one of the registers, well, not being set correctly, swapped some bits around and then could play Tetris. All right, cool, we made it work. So what's next? Because you never end, right? Well, a few years after the Game Boy was released, the next version came out with a little bit more colors than only 4. So I want to really add the Game Boy Color support. It's already partially in there, but most of the games crash, and you're also supposed to be able to play normal games, old games, in color mode. That also really doesn't work. So I want to make sure that that works. And there's also, there's 2 GitHub repositories at the time that I made the slides. One of them might be down now. But some people made unit tests for the Game Boy. So there are people that made custom ROMs to test specific aspects of the hardware of the Game Boy to see if your emulator emulates them well. Really cool. And I want to make sure that all of them run as well. What I also want to do, and I already tried to, but didn't get the success yet, is to make a Blazor version of this. Because why not? Make a WASM that you can integrate your Game Boy emulator and run it everywhere. Would be cool. It's not there yet because I can't make it work without threading support, and in Blazor, in .NET 6, Blazor threading support was not a thing. It's supposed to be added in .NET 7. I didn't have a look yet. Might take a stab later today, who knows. But I have 15 minutes left, and I didn't show you the emulator, which is a shame. So it's time to actually look at the damn thing and show you that it works. And we have Visual Studio. I press Ctrl F5, and let's open up a classic. Yeah, this is also something you're not supposed to do. You're not supposed to show the Nintendo logo, because that means you're emulating Nintendo's copyrighted software. Could be a little bit late to ask, but is there someone from Nintendo in the room? Okay, cool. NDC, your video might be pulled from YouTube after this one. We'll see how that happens. But you can just play the game. I'll turn the sound down a little bit. And you can run around. And you can watch me playing Super Mario. And because it's an emulator, you can play around with the sound as well. Let me actually first go back to the overworld, so that's a bit more fun. We can disable some of the channels so that it sounds. You can now find out how the sound works, and then you know you have the drum sample and the bass is a wave sample. And then you can turn it back on. Hi, come on. Voila, there we go. We have our full music. I am going to disable that boot run for now, because I want to run one more game, which is a very special game. It's the NDC London game. Not really a game, it's just Big Ben and The Clash playing London Calling. If there are fans from The Clash, I do apologize. It's only an 8-bit version of the song. I can only do so much with 8 bits. But I just wanted to show there's still a very active community around the Game Boy, playing around with making their own games. There's even someone who created a Unity-like studio where you can build games with code elements like in Scratch. If you know Scratch, you can easily script your game. Very cool. It also outputs the original. It outputs a C version, so you can go further in C if you want to. And there's also like a tracker music software which you can use to make music for the Game Boy, which is what I used to make this music as well. There's actually also a community using the Game Boy itself with something called Little Sound DJ, a game for the Game Boy, and then going live on stage, DJing and playing music from the Game Boy, which is awesome. But I also still have some time, so I can dive into the code a little bit. Let me zoom in just a tad here. So this is the main loop of the Game Boy. When you fire it up, you still have that cancellation token, which is going to keep on running until you switch off the game or start a new ROM. And then every time you go through the loop, you do a tick, which is that crystal generating a pulse to all the systems inside the hardware. And then after a tick happens, you might need to enable or disable the screen. And sorry, that was a bit too much. And inside that tick, what happens is, well, no, it's a bit small. There we go. You either do high DMA transfer or you do a CPU event. Then you update your timer, you update your other direct memory access, you update your sound, you update your serial port, and you update your screen. So everything gets a chance to run. That's really important. What's also important, which was also a big mistake that I made in the first time, if your CPU gets a chance to perform something, which is what's happening here, that doesn't necessarily mean that it will. My first version did this. I read an instruction. That instruction might need other data and even more data. So I read this, and this. I execute the instruction, and then my CPU tick was done. Wrong. Completely wrong. What you need to do is, if you access memory, that means that you had to wait on the clock, or the tick rather, to go up or down, because you need to wait until it's safe to read that actual memory, which means then you need to give the rest of the system a chance to run before you can do the next step, which might be fetching another piece of memory, waiting again, and then you can execute the actual instruction. So it's a bit more elaborate to make it really, really work. But in this case, it is keeping track of all of this. Also a little experiment to see which one is faster. Is it the for loop or is it the while true? Doesn't really matter because it's compiled down to the same thing. But here you can see it's fetching the opcodes and then fetching, in some cases, 2 opcodes, fetching the operands, and then only then it's running the actual instruction. And I must say, the original source code from the Java version was pretty well structured because it basically adds all of the instructions. For example, you get here register a load command, which is one of the LD instructions, and then you get 2 operands, or you get a jump, or you get an add, and then it's really, really nicely structured so that it all ties in together and you get small pieces that you can understand how they work together, which is really cool. And then your GPU, again, has those states where you go OEM search, pixel transfer, wait, I have to do this first, other way around. OEM search, pixel transfer, and then H blank, and then at the bottom you get V blank. So you have those modes here as well. And then you start executing, where is it? Here. So if you're inside a specific phase, OEM search and so forth and so on, you execute that phase until you hit a switch in state, and then you swap your modes and phases around so that every phase gets to work. And then, for example, the pixel transfer really is nothing more than filling a buffer with the pixels from the correct memory spaces so that your Windows Forms gets a chance to output the video on screen. Yeah. I could go probably another 4 hours talking about the code, but I only have 8 minutes, no, 7 minutes left. So I'm going to give you a chance to ask me some questions if you have any. Yeah?
How many hours have you spent working on this?
How many hours have I spent working on this? Way too much. I can try to look in the Git repository. I started with the best step, git ignore. And then to get somewhere workable is 11 July, no, sorry, 13 October. So that was a good month and a half, but also a lot of restless nights, because at some point, I actually think it's in here, 1:25 a.m. That might be my, yeah. It was still manageable. 1:25 a.m. was the latest at night that I was working on this before I realized maybe it's time to go to bed now. But yeah, I've spent several hours in this. If I would total it up, it's going to be easily 4 or 5 full-time weeks. And that's with a working example. Because what I did forget to mention is I did not just clone David's repository, but I put it next to mine and then compared what I was missing and doing wrong. And then I did copy it over manually, but also manually because then I forced myself to understand what was happening in the code base rather than just saying fork it and improve it. Because it's a bit different than what David is doing. I did send him a pull request for adding sound in his version as well. So to help him improve his version as well. No other questions? It's a bit of a niche topic. Not everyone is probably waiting to jump in and writing an emulator themselves, but I must say I had a lot of fun trying to do something like this. I sometimes get crazy ideas to do stuff. One of the other ideas is I started porting Doom to C#. Also got that running. It also runs on Maui, Doom. So we have Doom running on an Android phone using C#, which is cool. Okay, so if there's no other questions, then I have one more slide. Thank you. And if you want to grab the presentation, which includes all of the links to materials, also includes links to how to make your own Game Boy games and stuff, then you can find this QR code. But I'm sure we'll also get the slides via NDC back to you later as well. All right? Thank you and have a great rest of the conference.